Okay. So first of all, I would like to thank the organizers for this very interesting and multidisciplinary conference. So in this talk, we are interested in the relations between optimal transport and information geometry. Both fields are gaining a lot of attention in recent years. So I'm Leonard Wong, and I'll begin by telling you the background of this study, and my co-author Jiaowen will discuss the results. So here is a one-page reminder of optimal transport. So here I have spaces M and M prime. So here I let x-axis be the original space M, and the target space is the y-axis M prime. And I let C be a given cost function. Okay. So here I have an example where I have two discrete measures. So this is mu, and this is nu. And the task is to distribute, say, at each point, I want to distribute the masses from mu to masses to nu, so that the total transport cost is minimum. Okay, so this is called the Monge-Kandorich problem, and I want to minimize this functional. And in general, what I will get is an optimal coupling, which means that at each point, the mass can be sent to various points in y prime, in M prime. Okay. So this is the optimal coupling where the color shows you the different masses to be sent. In general, we get an optimal coupling. Okay. So, but under some nice conditions on the cost function and on the measures, it can be proved that, for example, when these are continuous measures and say the cost is the quadratic cost function, then we can actually prove that the optimal coupling concentrates on the graph, okay, of some optimal transport map that I call F. So in this picture, then the mass will concentrate on a graph, okay? And we are going to study the graph. So one way to look at the optimal coupling is to use the cross difference introduced by McCain. And here's the intuition. So suppose that this is the optimal coupling, okay? By the optimality of this coupling, what happens is that suppose I want to move the masses around to get another coupling. The optimality of this coupling means that no matter how I perturb the mass of the coupling, I always get a higher cost. Okay, so this is the intuition of the optimal coupling. And this is how we define the cross difference. So suppose that I take two pairs of points in the product space. So I have one pair and another pair. So in general, the 2 points can be anywhere in the product space, but here I show it where the 2 points are on the graph of the optimal transport. So the cross difference is defined as follows. So the first two terms is the cost if I transport P here to Q prime, plus the cost if I transport P prime, P0 to Q prime. Okay, so the first two terms is the cost of these particular assignments. And then I look at the difference between this and the assignment where I transport P to Q prime and P0 to Q0 prime. So this is called the cross difference. And in general, it can be positive or negative. But if both points are on the graph of some optimal transport map, then by the optimality of the transport, no matter if I switch the two transports, I mean the targets, I always get a higher cost. Okay, so this means that if the 2 points, the two pairs of points are on the graph G, then the cross difference is always positive or non-negative. Okay. So this functional, as you see, does not depend on the optimal coupling. It only depends on the cost function. Okay, and it's defined on the product space. Okay, it's defined on the product space. So now I want to define following Kim and McCain a pseudo-Riemannian geometry on this space. So the way to define it is as follows. So suppose that you think of this as one point, and this is another point. You can think of it as some kind of assigned divergence on the product space. So signed means that it can be both positive or negative. Okay? So suppose that I fix this point, and then I move this point. Okay? Then sometimes I have positive values, and sometimes I have negative values. And suppose that I fix this point, and I look at the Taylor approximation of this function about this point. Okay? Then the second order Taylor approximation of this functional, when I fix the second pair of points, gives me a function on the product space. Okay? And so this is the Hessian of this particular function, and it defines what we call a pseudo-Riemannian metric. So let me recall here that a pseudo-Riemannian metric is just like a Riemannian metric, except that it is not necessarily positive definite. Okay? But as we have seen here, along the graph, it has to be positive definite because of this inequality. Okay? So this is called the pseudo-Riemannian framework of Kim-McCain. The formula itself is not very important, but you should remember that it comes from the cross difference, which measures the optimality of the optimal transport. So here is a theorem by Kim-McCain which justifies this pseudo-Riemannian geometry. So I have the metric H, okay, a pseudo-Riemannian metric H on the products, and it allows us to define a Lefebvre connection that I call nabla bar, and also a curvature tensor. Okay, so the curvature of this pseudo-Riemannian metric is actually related to the so-called Mar-Trillinger-Wong tensor, which can be used to prove regularity properties of the optimal transport map. So one can use this geometry to see the regularity of these submanifolds. Okay, so this is the first geometry we talk about. Here's another way to think about the optimal transport map, and it is through the so-called Kantorovich duality. So we call this the so-called C divergence. So how to categorize the optimal transport map? In Kantorovich duality, we can categorize it by a pair of functions that we call the Kantorovich potential. And the property we need here is that, so we have a function, we have a pair of functions. One is phi and the other one is psi. One is on M and the other one is on M prime. And what happens is that the function, so phi of p plus psi of q prime is always less than the cost function on the product space, but equality only holds. So equality holds if and only if I'm on the graph of optimal transport. So this is very similar to the Legendre duality, except that the dot product on the right-hand side is replaced by the cost function. Okay? So actually, for the Legendre duality of the x dot y, and it corresponds to the quadratic cost function. Okay, so as you can see, I have an inequality which only an equality only holds on the graph of optimal transports, and in previous works we used this fact to define a divergence that we call a C divergence. So let's think about G as a submanifold of the product space. Okay, G is a submanifold of the product space, and as you can see, it's like diffeomorphic to the M, or it can be diffeomorphic to the image of the optimal transport. So given 2 points, x and x prime, on the graph, I can have a new point, p, q prime, where I take the first coordinate of the first point and the second coordinate of the second point, and then I look at this particular inequality. So the difference of, the difference of this inequality is always non-negative because of Kantorovich duality, and it is 0 if and only if I'm on the optimal the graph of optimal transport, which is when this new point is actually the same as both points. Okay, so this the inequality here is called the C divergence, and in some sense, you can think of the C divergence as the distance between this point and the graph of the optimal transport. So we call this the C divergence. So now we have two geometries on the space of optimal transport, and here let's just give 2 examples. The first is when I have Euclidean space for M and M prime, and I let the C be the quadratic cos. Then it can be shown that the corresponding C divergence gives you the Bregman divergence. Okay? It is because of Brenier theorem, which says that the optimal transport map is given by the gradient map of a convex function, which is related to the Bregman divergence. Here's another example where I have the positive quotient, and the cost function is like log of the dot product. The corresponding C divergence is called the L-alpha divergence and was studied extensively in our previous works. Some properties will also be mentioned by Jiaowen. And in fact, any divergence, no matter what divergence you talk about, can be realized as a C divergence by looking at a suitable cost function for the optimal transport. So we have two geometries. One is the geometry on the product space, and it is a pseudo-Riemannian geometry. And because I have a divergence, so I have the product space, and I have the graph of transport. So on the product space, I have the pseudo-Riemannian geometry. But because I have a divergence on the graph of optimal transport, I can use it to induce a delistic geometry. So on the graph, I have G, and I have Riemannian metric, and I have the conjugate pair of connections. And in this talk, we want to study, we review the connection between these two geometries. So just to give you our first result, because of the way we define the C divergence, it can be shown easily that actually the cross difference of Kim and McCain, if I restrict it on the graph of optimal transport, is equal to the symmetrized version of the C divergence. So this gives you an intuitive reason that the two geometries are very much related to each other. Okay? So now I'll pass the time to Jiaowen, who will discuss the main results of our paper.
Oops. Cool. Thanks, Leonard, for introducing these two geometries. In this slide, I'm going to talk about one of the main theorems in our paper. Before stating the theorem, let me firstly define, we have two projections from the product space M times M prime to the graph G. As you can see here, for any point X in the product space, you can project it vertically to graph G with pi 0, which keeps its coordinate in M invariant, and respectively pi 1, which looks like horizontally, keeps its coordinate in M prime invariant. And both pi 0 and pi 1 have images on the graph G. So these two projections are quite natural. And so we have two results in our main theorem. The first one is the information geometric G is actually the restriction of H on the graph G. And second one is the primal and the dual connections are also the restriction of the Levi-Civita connection in restriction on the graph G via these two projection map. So in the next slide, I will talk in details of how this projection is actually working. So let us take a local view of what happened in the graph G locally. So as you can see on the right-hand side, the blue surface is the graph G, and the gray plane is the tangent plane. So if we pick any two tangent vector x and y right here, you apply the Levi-Civita connection now blah blah on it, it gives you a new vector now blah blah xy, which is the black one, black vector here. Since the now blah blah is actually the connection in the product space, which is bigger than the graph G, so the new vector may not necessarily lie on the tangent space anymore. But however, we can project this new vector to the tangent space just by applying the differential of pi 0 and pi 1, which gives you these two green vectors. So these two green vectors are just the projection of this black one on the tangent plane. And our theorem just simply says that these two vectors are nothing but just the dual and primal and the dual connections of xy. So this states simply how you can by the geometry of the product space, you can project it to the graph and get the dualistic structure on the graph. And this result is quite general because this is true for any possible divergence. And it also gives you another point of view of how the dualistic structure is generated. And so now since we have studied the relations among the three affine connections, and it is natural for us to study the corresponding, to study the relations of the corresponding sectional curvatures of these connections. And just remind you that the sectional curvature is just giving you two tangent vector, and you have a sectional curvature value. And here we consider a special type of sectional curvature where these two tangent vectors are looking like one is a vertical direction and one is horizontal direction, and which is in this form in the product space, where x vanishes at the m prime coordinates and y vanishes at m coordinates. If these two tangent vectors are given like in this form, then we call the corresponding sectional curvature as the cross curvature. And we say like the cos function has constant cross curvature if the identity holds. This is as the usual definition. And this is one of our theorem in our paper, shows that if the cos function has constant cross curvature, then the corresponding dualistic structure also has constant sectional curvature everywhere. And another consequence is it also has constant sectional curvature on the graph G. So this is one of the relations of these sectional curvatures. And in the next slide, I will also have another interpretation of the cross curvature. Here, in this theorem, we consider, as you can see, the blue surface is again the graph G. And if you pick any point x on the G, and you consider two geodesics starting from x, one is the primal geodesic and one is the dual geodesic. And it is interesting to study the divergence between the geodesics, which is this d of gamma s and sigma t. This quantity has been studied for quite a while in information geometry. For example, if d is Bregman divergence or the L alpha divergence mentioned previously, then d has a generalized Pythagorean theorem, which means that the divergence between the geodesic, which is the yellow dashed line, actually equal to the sum of the divergence along the geodesic, as long as your two geodesics intersect orthogonally. So here we are interested in the mixed derivatives of this quantity. And we show that the mixed derivative at the starting point is proportional to the cross curvature. So as you can see on the left-hand side, this quantity is a pure information geometric quantity, which described by pure and a dual primal and a dual geodesic. And on the right-hand side, it is the cross curvature. And Leonard previously mentioned a cross curvature is proportional to the MTW tensor in the optimal transport theory. So actually, this theorem provides a new information geometry interpretation of the MTW tensor in optimal transport theory. And this is quite interesting and holds for any divergence. And so now our paper has a collection of theorems for general divergence. We also have some concrete calculations and examples for some specific divergence. Which is here, the L alpha divergence is actually the C divergence of the following cost function. And we calculate that it has constant cross curvature, which applies that it must, this divergence has, the dualistic structure has the constant sectional curvature. Which recovers Leonard's previous work. And also we calculate the mixed derivatives of the L alpha divergence, and which is equal to negative 2 alpha times the square of the inner product. And these results can imply that the MTW tensor of the L alpha, of this cost function vanishes identically, which also recovers one of Ken and John's work this year. So, this work, our paper actually brings a new bridge to connecting information geometry and optimal transport, and I feel like this connection is quite simple and straightforward. It helps you to understand how these two geometry are connected, and hope you enjoy it. Thank you. Oh, these are the references.
I have a question. So, on that's for previous yes. So, the divergence in this constant section, always constant in this always in this constant sectional curvature,
Yeah.
right? So, which means there is no dually flat structure in this framework because if alpha equals 0.
Yeah, if alpha equals 0, then which means this one is flat and this one is flat, right? Because if alpha equals to 0, then the L alpha divergence actually tends to the Bregman divergence, so it's dually flat. Yeah.
Okay.
Mm-hmm.
Question. When you have a divergent function,
Oh, what?
divergent.
Oh, divergent function.
Okay, the diagonal is Lagrangian. So that's it, right?
What?
When you have the divergence, we define on in cos down n.
Uh-huh.
Okay, we take the diagonal.
Oh, yeah.
Okay, you have a local symplectic structure.
Yes.
Yeah, and the diagonal is Lagrangian.
Yes.
Okay. You can extend this Lagrangian function by Lagrangian foliation.
Oh, I see. Yeah, it's possible. It's possible, and I think like we have some ideas on that, but it's possible that you can extend by violation from a divergence on the diagonal and for all the space, right? Yeah, it's possible, but we haven't make through of it. Yeah.
You know some? Can you ever case it possible?
No, we try, but it's not always possible for that.
It should be possible if your manifold has local effect structure.
It's like if you can have like isomorphism of the graph, and you can for all the spaces, then you can extend. You can have divergence everywhere. Yeah, that's true. Yeah.
So now given a cost function, and you can try to find G, and you have a deformation structure on G. Now the question is first, given M prime cross M, and given a graph G with the statistic structure like this, so can you this correspond to the cost function? So this is inverse question. So given G and the statistic structure on G, okay, so on the graph. So can you find a cost function corresponding to this structure?
Oh yes. This is actually first done by Amari, which is so-called a canonical divergence, which giving you a dualistic structure, can you find a divergence such that it induces this structure? And this is true. Amari gives a simple construction. And here in our framework, and also in our last section of paper, we offer a new point of view of how to look at a canonical divergence. It's just like since you have geometry along the graph G, then how you find the cost function is just equivalent how you extend how you extend the geometry along the graph to the whole space. Yeah, if you find this extension, then you find the cost function. Yeah, they are equivalent. So that's in our last section of paper, we also offer this point of view of how to. It should be a new point of view to look at the canonical divergence problem. It's just an inverse problem of this.
Thank you.
Cool.